Let me also start with thanking the organizers for having me here at this very nice, exciting meeting with many old and new friends in the community. I would like to share some of our recent work on surface acoustic wave devices, technological work on how to fabricate IDTs, and especially high frequency IDTs, and some experiments, partly done in collaboration with the group of Paolo and Alberto, and some outlook of the experiments we like to do in the framework of the Soul Train network that we are part of, and Robert Ukropets, who was presenting a poster just till 5 minutes ago when the poster was taken away, is also here. And we have another PhD student who will start this month also on the topic. So let me start with a prologue, and already referring to someone else here in the audience, Fujisawa-san, because this is actually the reason why I'm standing here today, and also had a huge impact, basically not only on my scientific life, but actually life in general, because in 1998, Fujisawa-san was visiting Delft, and I was just starting as a young PhD student, and I had the luck to join these very exciting experiments that Fujisawa-san was doing on double dot systems, and especially looking how a double dot system, a two-level system, interacts with its environment, with its particularly its phonon environment. And the idea was that defining by top gates a double dot system and looking at its peak shape, its current shape, especially looking at the elastic transport, so corresponding with zero detuning, you could see the elastic current. But more interestingly, even at zero temperature, you could see an asymmetric tail corresponding with spontaneous emission of what we found out later, phonons into the environment. And at zero temperature, or effectively zero temperature, the absorption side is zero. But if you somehow increase temperature or you excite on purpose phonons, you would expect also to see something there. So at that time, from the temperature dependence, basically, we could deduce that already acoustic phonons were the main cause of this emission tail. So the follow-up idea was, could we play with this spectrum? And we got the idea, well, maybe we can make a cavity. And that was going to be the topic of my internship at NTT BRL next year, 1999. And we made some samples, actually. I think that's the first time I met also with Paolo. Of course, Yamaguchi-san also here in the audience. So the whole thing started to move on from there. We didn't really succeed in making these cavities, but you will hear more about it this afternoon from Fujisawa-san, because I think he is closing the circle there. But sometime later, quite some time later, we did a kind of the reverse experiment, again in collaboration with Fujisawa-san and Ryu-san at NTT, where we made again a double quantum dot, but then instead of suppressing or filtering phonons in a cavity, we produced surface acoustic wave phonons on purpose in the environment of the double dot by this IDT, designed in also after long discussions with Paolo at NTT. And what we could see is that indeed at resonance of the IDT, we could basically get phonon-assisted transport from one level to the other, either by absorption or stimulated emission. So that worked very nicely. The only thing is that we couldn't really resolve the phonon sidebands, because the frequency that we used for the IDT was somewhere close to 2 gigahertz, corresponding with 8 microelectron volt. And the elastic peak width of the double dot that we had, so this ground state line, that was about 14 microelectron V, so larger than the actually the sideband separation. And well, that's not really a fundamental thing. It was, I think, an experimental shortcoming, because in principle, the nice thing about a double dot two-level system is that you can kind of turn off the temperature. So especially if you tune it in this configuration, large bias, the Fermi broadening of your source and drain levels is far away. So in principle, the line width is only determined by the line overlap of these two levels. So you could, in principle, have a resonance, an elastic current width that is smaller than temperature. But okay, in this experiment, didn't turn out so well. So you could definitely see the side lobes, also the Bessel function modulation, but not really really individual sidebands, and go fully in the quantum regime, if you like. So there was already kind of need for higher frequency, or we could maybe also have improved on the two-level system. Okay, so that's kind of the prologue. This is how I came into the business and always kept this interest for surface acoustic waves. Now we're talking quantum acoustics. So again, as was already alluded to a number of times during this workshop, you really like to be in a regime where the quantum is larger than temperature, or at least another relevant energy scale like this ground state energy overlap. So we started thinking at the time when I was then in Twente about how could you really go to high frequencies and go into the interesting regime, which is of course for this quantum community interesting, but also high frequency is very interesting for maybe more mundane applications like high bandpass filters in telecommunications and so on. So in general, high frequency surface acoustic waves are interesting for a number of scientific but also technological reasons. Okay, well, this introduction has been given now a number of times and probably much better than I can do. I just want to refresh your memory after a couple of beers yesterday in the bar. So again, the surface acoustic wave is a kind of nano earthquake, which is a combination of longitudinal and transverse motion. And we call this this in-plane elliptical motion we call a Rayleigh wave. It propagates along the surface with the surface acoustic wave sound velocity. And as was also explained yesterday, this mode tends to stay near the surface, has the lowest energy there, and the energy and field displacements are concentrated within roughly 1 lambda from the surface down into the substrate. The amplitude is normally relatively small, the mechanical amplitude, in the order of 1 nanometer or smaller. The interesting thing is that the surface acoustic wave sound velocity is much lower than the electromechanical or velocity of light in the medium, so the electromechanical velocity with well, a factor of 100,000 or so. So that's why you can use surface acoustic wave as a kind of delay line in a circuit. That's also how you can actually time separate direct crosstalk electromagnetically from acoustic crosstalk. So this very distinct velocity, propagation velocity, also sets a completely different length scales for the wavelength. So that makes the wavelength for surface acoustic wave typically on the order of microns, much smaller than for electromagnetic case. So that makes surface acoustic waves for a number of reasons very, very interesting. Also, again, specifically in this field of quantum acoustics. Okay, so you have this this displacement, this Rayleigh wave, and the interesting thing is that now you have regions of tension and compression, and this has two results. There was, and this I borrowed from Sanada-san, you have the local strain, which gives you both a band gap modulation and a piezoelectric field modulation, if you of course have a piezoelectric substrate. If you have a piezoelectric substrate, this effect gives rise to type 2 modulation. So this is the dominant modulation that you also see in this graph, the solid lines on the order of 100 MeV or so, and much smaller that is coming from the deformation potential. That will be this dotted line, which gives you a type 1 modulation of your band gap. So now it depends on the kind of experiment you like to do with the surface acoustic wave, what you like to benefit from. So Paolo explained yesterday in the first talk that he would like to have this axion transport, so you like to keep the electrons and holes relatively close together and not to lose the Coulomb interaction. But later on I will tell a bit about electron-hole transport, where you actually like to spatially separate electrons and holes, and you benefit more from a type 2 kind of modulation. So that's the brief wrap-up. So I focus now on piezoelectric substrates, and what we can distinguish there is this piezoelectric effect. If you have your surface acoustic wave, it leads to deformation. If you have a piezoelectric substrate, this will result also in an electric potential by virtue of this direct piezoelectric effect. Turning this around, it means also if you apply an electric field, then you can benefit from the so-called converse piezoelectric effect and turn this electric field into a deformation and produce stress and or strain. And as we'll see, you can also generate surface acoustic wave in this way. So that is the reciprocity of this effect, and that you can apply for generation of surface acoustic wave using so-called interdigitated transducers. These are these COM structures that you have seen a number of times now. What the idea is that you apply an alternating RF electric field to these two finger COMs, and by alternating, you create an alternating field in spatially, but also if you apply an AC signal also in time, and thereby you periodically induce strain and can produce a traveling wave out of the IDT, in principle also on the other side. There are all kinds of sophistications on this design. So this is the let's say the most fundamental idea. You can work to some people use a double finger design to reduce internal Bragg reflections in the IDT. I'll also show later a floating gate concept where you have kind of floating fingers in between, which help to make the IDTs more unidirectional. But the general idea is that you create this alternating electric field. Then the kind of standard way of characterizing the performance of these IDTs is by fabricating two of these IDTs, same fabrication parameters, opposite to each other, and do a so-called S-parameter analysis of it. So you look at basically a traveling surface acoustic wave from the sender to the receiver. You see what the transmission is. You can also look directly at the reflection from a single IDT, so what power gets in, what gets reflected, and in this way you can determine all these S parameters, in particular the transmission and the reflection. So this is an example of this double dot paper I showed before. So that's a kind of the bread and butter of surface acoustic wave generation by these IDTs. And well, of course, there's plenty of lithography techniques available to make them. Depends also in what frequency regime you would like to work. So you could quite well work with optical lithography if you're interested in 10 to 100 megahertz regime. If you want to go to more like 100 nanometer regime or below, you have to go to nanolithography like E-beam. That's what we did for previous work. But it's quite tedious. The point is that on one side you have to make very small scale features. So your fingers, if you go into in 100 nanometer regime wavelengths or so, the individual fingers need to be on the order of tens of nanometer. But at the same time, to get a sufficiently large quality factor, you need to have many of those fingers, order of hundreds, over typically tens, hundreds of microns or so distance. So that's quite challenging for E-beam lithography, things like proximity effect and drift over time. So we started thinking about an alternative method. Now I thought probably I don't need a lot of time here in this place to convince you why printing is a good idea. I think you will be completely exposed to the story tomorrow during the excursion. But of course, the revolution brought by the book printing, by the book press, was that it was much faster than, let's say, the serial writing of the monks. Made it thereby much more economical, and also reproducibility came into the play. So a couple of years later, there was proposed by Professor Chu and maybe some others a bit earlier, but I think his name is mostly associated. Like there's also a Dutch guy who is associated with the invention of the book press, but I don't want to go into this discussion at all. But basically the same idea of having a template and stamp it. And now it's not so much an ink, but the general idea is, well, it basically brings you back to kindergarten. The general concept is very simple and elegant. You have a mold or template or stamp, as it is called, and you stamp it, you imprint it in a soft material. So typically this is a polymeric material. And then you see the protrusions on the template will be then imprinted in this soft material, and you will get basically kind of the reverse image of your template. The nice thing of this technique, and there are many things about it that are not so nice, but let me stick with the nice things, is that once you have your template and you have your features there, you can basically imprint it many times, no matter on what kind of substrate. If the substrate is flat enough, then you can, it doesn't matter whether this is silicon or gallium arsenide or lithium niobate or graphene or whatever, you follow the steps of this imprint, and then you can reproduce your features. That's much different for example, E-beam lithography, which would be kind of direct competitor, where you have to adjust like dose and writing speed, things like that, depending very much on the substrate, whether it's conductive or insulating or not. So that is a very nice feature of nil. The big disadvantage is, of course, that it's not very flexible. Once you have the template, this is it. If you want to change your design, you have to get a new template, and normally they are not so cheap, especially if there's many nanoscale features on them. Okay. Yes, please.
I mean, I don't know much about nano increasing, but the mold you still need to fabricate with E-beam lithography, or how do you fabricate?
The template? Yeah. So normally that's indeed E-beam lithography. It's like also how the optical masks for the big wafer steppers are made. First you need the e-beam lithography, which is expensive, is slow, but at least you only need to do it once, and then you can make many copies. Very, very much in analogy to these letters here in the box.
How many times can you use the template before it wears out?
Yeah, so I think it's on the order of few hundred times or so. It depends a little bit on how well you pamper the templates, and you clean them, and if there are impurities on your substrate, you may induce defects on it. So yeah, you really have to pamper them. But yeah, as far as I understand, then you can use them a couple of hundred times or so. Yeah. Yeah. So the real specialist in Twente is Boris Vratsov. He is hired as a senior technologist at the institute. He also has his own company, and he is also part of this Soul Train network that I mentioned in the beginning. So, well, again, this is the general imprint strategy. Here, a little bit more sophisticated explanation. So you have your template. Normally, you have to put an imprint resist, and you have to adjust the amount of imprint resist depending on the features on your stamp. So this is not completely trivial. So there's an algorithm how to dispense this. Then you imprint. In this particular kind of nano imprint lithography that we use UV cured curable resist. So what you have to do, you imprint, then you expose to UV, you cure the resist, and then you retract. That means that the stamp needs to be transparent for UV. And so we normally use quartz for that. There's other techniques like hot embossing where you do a heating step. And then you retract, and then you have your replica. Well, that sounds simple, but there's of course a lot of tricks, especially also in the next step to come, because now it depends on what you want to do. Now you have this features. You have the residual resist layer. So you could think of now doing an etching step, an oxygen plasma, for example, to remove this residual layer. So the protrusions will stick. They will be reduced a little bit in height, but you will expose the substrate. And after that, you can do standard metallization and lift off, or you can use this resist as an etch mask and etch. So from there on, you would do your regular lithography steps as you would do them for e-beam or optical lithography. So this is the machine that we have in Twente. It's a machine from Molecular Imprints, Imprio 55. And the nice thing about it is that it's a so-called step and flash machine. So on a wafer, you can make multiple imprints as shown here. The alignment is not super duper that you can align within like a wafer stepper, but at least you can make a number of copies on a wafer. And we, as you will see, we will combine that then with other lithography like e-beam or optical lithography that you can align to your imprinted features. Normally that's the order. First the nano imprint, and because you need to have very flat surface for that, and from there on start to continue your fabrication process. So Serkan Büyüköz was a PhD student in Twente who dedicated his PhD life to working on IDT devices produced by NIL. After that, he moved to Paulo's group in Berlin, and presently he is in Turkey, has a position there. And he designed, in very close collaboration with Paulo, also these templates having many different IDT structures. So all these blocks that you see here are basically full IDTs or IDTs coupled facing each other with different feature size. So the smallest feature size that we have used is 65 nanometer spacing and finger width. So that gives the smallest wavelength of 260 nanometer. You see we have all kind of different geometries allowing for all kind of experiments. So we have used a slightly different technique from the standard imprint lithography, so-called reverse process of the step and flash imprint lithography. So the first step is the same, so we imprint in imprint material, but after that, so this is an organic layer, kind of, well, this in this case, a polymer again, but then we we spin on another organic-based silicon-containing material called HSQ, hydrogen silicate equoxanate. I prefer saying HSQ, which is used as a planarization layer, and will also result in an inversion of the pattern. And I will explain in a moment why this is beneficial. So instead of moving on from here and then just remove the residual layer, we first planarize with this HSQ, so spin on, and also we actually imprint with a flat stamp to further planarize this HSQ so that we can get really a very nice flat layer on top. So the results, it's maybe not so very easy to see, but here you see the imprinted features. There is somewhat planarization, but still here that says 40 nanometers, some variation on top. Here also you can see that it's not really fully planarized. And also again, the degree of planarization depends on the features there. If you have larger feature size or larger spatial separation, this planarization gets worse. So that's why we added this idea of having a flat substrate. So it's basically a double-sided polished wafer that you can push on to this HSQ layer and thereby improving the degree of planarization. And here you see a number of results for different pressures, and probably this gives the best contrast. You see that you really get a very nice planarization there. You have here the organic resist protruding, here this HSQ layer. So now what's the result there? If you if you have the planarization factor defined as follows, so you look at the initial step height of your features, which in this case are on the order of 150 nanometer or so, so this imprinted features, and you compare then what this planarization is after just spinning on. You see that, of course, this is already far reduced, but still in the order of 10, 20 nanometer. But if you do now this flat wafer imprint, you can really get to sub 10 nanometer. Yeah, the figure of mirror there is the so-called degree of planarization, which is after this pressured flat wave is close to 1, both for 100 nanometer scale features, but also for larger scale half micron features or so. So that works very well, and of course this is a technology that is you can use for all kind of fabrication where planarization is an issue, not necessarily nano imprint lithography. So we also use it for completely different purposes because it works so nicely. Then here comes the motivation for doing this step, because once you have your features in the organic layer and you have succeeded in making this very nice and planarized, you are able to etch back the HSQ down to these organic features. So we use a fluorine-based plasma to etch back the HSQ till the moment that these features start to appear. So now you have basically a kind of silicon oxide material, this HSQ, which is in a sense inorganic, and then you have these organic features exposed. If you now continue with an oxygen plasma, you only make the HSQ more resistant, because you even further oxidize this HSQ, but you remove the organic material. And the reason why that is very nice for us is that we can keep the critical dimensions of the imprint, because they are determined by the initial imprint, and therefore also finally by the width of this HSQ feature. So now again the reverse. But we can, this plasma etching is now not non-critical while maintaining the critical dimensions, and even more so we can over etch a little bit in this oxygen step and get an undercut. So those are two features which are very important, we think, for maintaining the critical dimensions. So critical dimension is maintained, and finally this undercut feature allows you to do lift-off metallization and lift-off much more easily than if you would use the direct processing. So that's very advantageous, and probably one of the key factors why we can get to such high quality IDTs using this method. So here you see a number of SEM images of these fingers or test structures, and you clearly see, depending on the etching time, you can have more or less undercut. So this is a bit longer etching, and you really see that at some moment even you start to remove completely the organic material. So you have to be also careful there. But the good thing is that no matter how long you etch, this width is constant in principle. Okay, so that's about how we make the things. Now about the substrate. So like I said, in principle, you are very substrate independent, and you're quite free in choosing your substrate therefore. You have seen a lot of examples of obviously piezoelectric materials. Gallium arsenide is very, very nice. Lithium niobate, also very high electromechanical coupling. We are interested to move to silicon systems, also for doing acousto-electric transport in silicon, and hopefully also quantum information processing in silicon. So we like to combine surface acoustic waves with silicon substrates. And there you have your problem, because silicon, as you know, is not piezoelectric. You can, of course, take advantage of the deformation potential, but that modulation is much smaller. So what we need to do is to fabricate a piezoelectric layer, at least at the site where we want to generate the surface acoustic wave and also where we want to detect them. And if you need the piezoelectric potential also at your device of interest, you would also need your piezoelectric there. So what we have done is, starting from a silicon wafer, which is in this case rather standard. It's double-sided polished because we need that for the imprint, but it's pretty low resistive p-type, so it's not really highly intrinsic or so. Just to show that the process in principle even works for rather straightforward silicon. What we have done on top of the silicon is having a silicon oxide layer there, and then come with a zinc oxide piezoelectric film, deposited there by sputtering. So the buffer layer is there to increase the electromechanical coupling. I'll show that in a moment. And the nice thing about, which is a kind of side bonus that you get if you have multi-layer system, is that if you have a sharp variation in the elastic properties, or let's say the surface acoustic wave velocity between the different layers, you can also excite higher modes. So you get a kind of wave guiding in the system. So that allows you also to go beyond standard modes and go up to higher frequencies, as we'll see in a moment as well. Okay, so that's the substrate, and after that the imprint story is basically the same as I have explained to you previously. Here's some characterization of the zinc oxide. This was sputtered at Izmir Institute of Technology. And what you see is that the dominant crystallinity that you can observe there is the 002 peak, which is corresponding to the C-axis, so perpendicular to the surface. So what you do is you grow a polycrystalline film by this sputtering, but the good thing is that the word side symmetry has the lowest energy, so the tendency is to really have the 002 orientation, despite the fact that in plane the grain size is on the order of 50 nanometer. So that is good for us, because the C-axis oriented zinc oxide gives you the good piezoelectricity. And this other 100 peak probably has to do with this polycrystallinity. Yeah, but you see this 002 is the dominant one. So we can get quite smooth layers in this way, on which we can continue with the nano imprint lithography. So here are the results already on top of the zinc oxide. And as I said, we vary on the mask between 65 nanometer features. So this would be 260 nanometer wavelengths, 4 times this for single finger design, up to 125, 500 nanometer wavelengths. Okay. So here you have the data. The important thing is you see here the different wavelengths. You see also the number of fingers. So you really see there are many, the order of 1,000. The opening, so the aperture means how basically what the aperture is for the traveling wave is 30 microns, and the distance between them, we have 2 different distances on the order of 0.5 millimeter and 1 millimeter. So they are far apart. As you know, surface acoustic waves can travel coherently quite a distance along the surface. Okay. So doing this S-parameter analysis, measuring transmission. This is the transmission. Here are the blue and the red curves. So the blue curve corresponds with 405 micron separation, the red one with the largest separation. As you can see, they differ, but the attenuation over 0.5 millimeter is not dramatic. And what you can see here for the different wavelengths of 500, 320, 400, 260 is both in the reflection and in the transmission. You see these sharp features that correspond with the surface acoustic wave resonances, in particular with the fundamental Rayleigh mode. So this is this elliptical motion, but also higher modes, higher Rayleigh modes. So these are not higher harmonics of the fundamental, but these are really different modes. I'll come to that in a moment, that come into being thanks to this multi-layer design. So, and the reason why we know this is because we have done finite element COMSOL simulations where we can assign those peaks to these specific modes. I'll show that in a moment. Yes?
I guess in these measurements you are subtracting the baseline, or you are calibrating the data.
Yeah.
I see that your baseline is extremely fast.
Yeah. Yeah. So there's indeed a number of calibrations / tricks there. So first of all, when you do this S-parameter analysis, you have to do a couple of test calibrations on a 50 ohm edge, an open, closed, so that you need to do. And I think this is also a so-called time-lapsed experiment. So you measure in time, and then you calculate back to the frequency domain. And in this way, you can nicely separate between direct crosstalk, electromechanical crosstalk, and the real acoustic signal. So there has been some analysis on that, yeah, to make it clear. That's true. Does that answer? Yeah? Okay. Good. Right. Okay, so a few more words on these higher order Rayleigh modes. So they normally appear when the acoustic velocity in the overlay or overlayers is lower than in the substrate. So that's the case for us. Of course, already in the design that was taken into account, silicon has the largest surface acoustic wave velocity, larger than silicon oxide and also zinc oxide. And well, the exact resonance frequency is dependent on basically you could say the ratio between the piezoelectric film and the surface acoustic wavelength. So it depends really on what design you use, where the Rayleigh modes come. what we see is that for the different delay lines, so 1 to 4, this corresponds to from 500 nanometer to 60 nanometer, we measure different modes. Sometimes we even don't measure the fundamental mode at all, because the electromechanical coupling is very small for this fundamental mode. But for, let's say, the smaller device, smaller wavelength, we can measure up to the highest Rayleigh modes, where the difference is really coming from the different velocities for these different modes. So the different velocities for the given geometrically determined wavelength give us then the different resonance frequency up to 16 gigahertz in this case for the fourth order Rayleigh mode in this multi-layer system. So what do they look like, these Rayleigh modes? These are the results of the COMSOL finite element calculations or simulations. Here you see the displacement for the fundamental, for the R1, and this is for 500 nanometer. So you see here that mainly overlaps with the zinc oxide. So the overlap is important there. Here you can also see why it's relevant, what is this ratio between the piezoelectric thickness and the wavelength is. If you go up to the second, third, you see that you get basically for every higher mode you get another node in the Z direction. So there's no node here there's one, here there is two, and so on. So, and based on these simulations and the frequencies that follow from them, we can assign also the experimental modes that we observe. Here is also the highest, this is 260 nanometers, so the smallest wavelength. There you can also see them. Okay, this is the comparison between the calculated or the simulated values and the measured ones. So here you see frequency, the acoustic wavelength, and these numbers correspond with the fundamental first, second, or third mode, Rayleigh modes. And you see, normally speaking, the agreement between simulated and observed values is very reasonable. Okay, so that was our basically first trial on silicon with a piezoelectric layer. Based on those results, there were a couple of improvements that we wanted to incorporate. First of all, if you have zinc oxide not protected, this is CMOS incompatible. Zinc oxide is also quite a tough material to work with, and very fragile and corrosive, basically. So we first of all try to make it CMOS compatible and also make our life a bit easier by putting a silicon oxide capping layer, just a small one. We adjusted a little bit we basically decreased the zinc oxide thickness to make it more advantageous for higher frequency Rayleigh modes, because they stick closer to the surface. And the last thing is that we went to, in this case, a highly resistive silicon wafer, so kind of quasi intrinsic silicon, because as you know, as long as you have free carriers around, they will screen the piezoelectric potential. So the more intrinsic your substrate, the better it is, at least for from the surface acoustic wave piezoelectric potential point of view. And again, the design parameters are the same. Why? Because our template was also the same, and their flexibility is 0. Okay. Same story. This is basically what I just told you in words. Characterization here. I think this zinc oxide was sputtered at PDI in Berlin by Paulo and his co-workers. And again, also here you can see that, at least for the zinc oxide part, the 002 orientation is dominant. Of course, here now you also have your silicon peak. You have also there the capping layer. Okay. The experiments were, again, the S parameters, the transmission and reflection data. This is for lambda is 1 micron, so that would be a double finger design with spacing a feature size of 125 nanometer. So there you have to double the wavelength. Also here you can see Rayleigh modes. This is the fundamental, this is the second mode, but also what you see is harmonics, third and even fifth harmonics of Rayleigh modes. So these are the more conventional harmonics, but then of the different modes. There, notable, of course, the transmission and reflection data are not astronomically good, but still recognizable is that we can find resonances there over 20 gigahertz. So there you're talking about 100 micro EV or so. So it's a Kelvin. Okay, so that was still kind of basic characterization, but we learned a lot of that. If you now go to a bit more in the direction of charge manipulation and acousto-electronics, there was this experiment done with Alberto, who is also here, and Serkan at PDI, and there the experiment was that we had gallium arsenide nanowires deposited on lithium niobate, which is a very strong piezoelectric material, then excite the surface acoustic waves using our IDTs in the lithium niobate, then basically use the piezoelectric potential straying, escaping from the lithium niobate into the gallium arsenide to pick up electron hole pairs generated optically by laser, as in this cartoon. So basically the motivation there is that you can have a kind of contactless charge manipulation, or in this case even electron hole pair manipulation inside nanowires. So that's very nice and elegant, and why particularly with this high frequencies I'll come to in a moment. But the important thing is that the surface acoustic wavelength is smaller than the critical device length scale, which is in this case the length of your nanowire. So imagine that the surface acoustic wavelength is comparable to the size of your wire. You basically have a quasi-linear potential over your wire. So the wavelength is very slowly varying compared to the wavelength. So that to the nanowire. Sorry. So that means that electrons and holes basically would move in different directions of this more or less linearly varying potential. So what we like to have is a very rapidly varying potential, as in this cartoon, where you really can transport electrons and holes, even spatially separated by the wavelength, in the same direction along the nanowire. So instead of having them going in opposite directions. Okay, so we benefit from this type 2 modulation. So this is piezoelectric potential dominated potential, coming not from the gallium arsenide primarily, but from the lithium niobate beneath, and then move this optically excited electron hole pairs along the wire. Then on purpose there is recombination centers there implanted to get again photoluminescence out. So there's no metallic screening of the piezoelectric potential, but in this case recombination centers. Okay, so there's Alberto, who worked on this before. There's also other people where always the surface acoustic wavelength was on the order or even larger than the length of the nanowire. So there you have this gradually changing potential. Alberto showed transport, quite high efficiency there, but also there the surface acoustic wavelength is longer than the nanowire. So we are in the opposite regime now by virtue of the smaller wavelength of our surface acoustic wave. These are a few more details on the nanowire. So it's used by this vapor liquid solid method, gallium arsenide, MBE. What is important is that you have this protective alga shell, which prevents non-radiative recombination, and also this inclusion of this recombination center, this in-gas structure. And typically the length of the wires is on the order of 7 micron. Okay, so this is the experiment. Let's see if I can share this multimedia show with you. Yes. So they were done at Paulo's lab at low temperature, 20 K, using the following setup. So the idea is that you have your laser, which is chopped at the frequency also of your surface acoustic wave. You excite the electron hole pairs. They then are picked up by the surface acoustic wave, transport along the wire, and there they are forced to recombine in these recombination centers. Okay. We used a particular design that was also on the template. It's called the Floating Electrode unidirectional transducer that I already alluded to in the beginning. It has these really floating fingers and varying width, which help to make the IDT more unidirectional and therefore also put more power into the surface acoustic wave. So in order to enhance this evanescent piezoelectric potential that needs to overlap with the nanowire. So the mode that we used for this experiment is corresponding with a wavelength of 2.6 micron, which therefore allows that we can really follow this picture of the cartoon, moving electrons and holes in the same direction. Okay. This measurement shows that if you have no surface acoustic waves and you completely expose the whole wire, so it's not just a point but just a kind of defocused beam, you see that you excite and you see also recombination of the gallium arsenide and a bit of this indium gallium arsenide center. So there is photoluminescence basically. If you now apply surface acoustic waves on resonance and you compare that with the off-resonance case, so where basically the surface acoustic wave is not interacting with the gallium arsenide, you see a sizable reduction of the photoluminescence, which is because you carry away these electrons and holes. So that works. Of course, the experiment that we really want to do is moving them around. This is another type of nanowire where you really have a point, a focus point of your laser. You excite your electron hole pairs here, and then you move them with the surface acoustic wave to the recombination centers. So there's one here that already is there due to simple diffusion. This is the center A, so even at low surface acoustic wave power, it's there. But, if you now turn on your surface acoustic wave, you see also another center appear that wasn't there without surface acoustic waves, and that shows that you can really transport your electron hole pairs unidirectionally in this case. Okay, I'm going Now a little bit to the outlook, and the future is robots, part of the saw train network. The idea now is to use this technology for all kind of experiments. Like I said, the technique is quite generic. You have seen this beautiful work on gallium arsenide so earlier today of Chris Ford's group. Things like single charge pumping through quantum point contacts, maybe even light generation. Try doing that, these things that have been shown or partly shown already beautifully in gallium arsenide. Try to do this also in silicon. And of course, there's a number of complications that come in there as well. Indirect band gap, things like that. A lower effective mass, all kind of things. But here you see a couple of samples that are now being made, and Robert likes to work on in the future, among other experiments. Then we also collaborate with Flores in the group, co-organizer of this meeting. He has basically introduced to Twente a very beautiful technology to make CMOS compatible silicon quantum dots. He also basically made, together with Philip Muller, these ambipolar quantum dots. So these are silicon quantum dots that can be at the same time be operated as electron as hole dot. The idea is that you have a silicon substrate, basically highly intrinsic substrate. You induce the quantum dots by a lead gate, and having, in addition to that, perpendicular to that, barrier gates that are insulated from this lead gate, and thereby having here this in accumulation regime and a very small puddle of electrons. And then, depending whether you apply a positive or negative gate voltage to this lead gate and to which of the reservoirs you connect, either p-type regions or n-type region, in this case you can define electron or hole dots and get very close to the single charge regime. So this is very, very nice and intriguing work, and what we like to do is to combine our surface acoustic wave technology with that. So here you see the Coulomb diamonds both in the electron and in the hole regime. Beside that, we also work on nanowires. These are also now group 4. So this is germanium silicon core shell nanowires. They are grown in the group of Erik Bakkers. Very nice, high quality wires by now. And what you see here is with many gates we can define dots of different sizes, and you really see very nice, beautiful Coulomb diamonds that scale with the length, or inversely Coulomb charging energy as you would expect. Very stable. Here you see a measurement over 30 hours or so with only very few switches, and beautiful, mesmerizing Coulomb diamonds. The idea is to start define also qubits in those systems, electron spin qubits. So what you like to do is define a double dot, which we have been able to do, in particular Matthias Brauns, who is now postdoc after doing his PhD in the group, and he has shown this textbook-like transition of a large single dot to the honeycomb stability diagram in these nanowires. And also relevant for spin readout manipulation, also the first observation in our systems of a Pauli spin blockade. So if you're interested in details, there is a paper coming out on that soon, hopefully. Okay, with that, I like to wrap up. So I've spent some time in hopefully explaining and convincing you the question that was asked already a number of times earlier: how are you able to get to such high frequencies? I think the answer to that is critical dimension control combined with this multi-layer design. Some examples of multi-layer structures, 16 gigahertz, but also going up to 23. Some example of an acousto-electric transport experiment. Thanks for your attention.
Do you see any scattering to the large quantum mode, especially in the higher order?
I'm not sure whether we observed that. I can't recall that we suffered from it, but I'm not 100% sure whether we saw signs. I think it was not a big hindrance for us bulk modes.
So compared to even lithography, the nano imprint method is also complex in terms of chemistry and so on. How big is the advantage? In principle, I think you could use even lithography to get these nice figures out.
Absolutely, yeah, you can do it. It's okay. So I listed a couple of advantages. There is also the disadvantages. I think what is really nice is not just the imprinting itself, but also that we have this recipe of inversion, this critical dimension control. I think is very, very nice. You get really very nice uniform features of the fingers. Maybe you could think of a fabrication sequence where you can also do that with e-beam. I think the other nice thing is really the substrate independence. So once we have optimized it, we can do it on, we don't need to worry about that. I have a personal experience at the NTT e-beam system writing these things, and you really have to leave them for a number of hours to write all these fingers. And yeah, if anything happens, if there's a hiccup or something goes wrong, then yeah, you can start over again. So I was personally quite happy with it. It won't be a very good method for large-scale production, though. So I think for small volume, I think it's quite attractive. Once that works, probably if you go to the EPCOS or so, maybe they would again go to the wafer stepper anyway. But
So in the slide 25, you were showing the casting chart. Yeah, so I was wondering how you experimentally measure K-squared.
Yeah. So what you can do is, I think it was done by comparing the two different separations. We have IDTs at the two separations, and then you can do the analysis, get it out. Yeah, that's a good question.
So from the data you showed at several different frequencies, you could, so in the transmission data there you can extract the propagation losses as a function of frequency.
Yeah.
Did you do that?
Yeah.
And did it follow the scaling, the predicted scale?
Yeah, so it goes indeed quite a bit down. I think I didn't include this graph in the presentation, but in the paper there is, I think it is nanotechnology paper. We have indeed the decay with frequency, and I think that is as expected. I can show you in a moment the graph. Yeah. That is, I think, pretty aggressively, maybe even exponential. I have to check. Yeah.
You mentioned that you synchronized the laser transport experiment with the nanovalue with the surface acoustic wave.
Yeah.
Do you see a dependence on the phase relation between laser and surface acoustic wave?
There, Alberto has to help me out. Yes. Do you see that, Alberto?
There is a dependence. You can select the phase, or whether the laser arrives when you have a maximum or minimum of the potential, and you can see a change in the delay of the time of the emission of the light.
But I guess this is only relevant if the laser is focused to a size smaller than the wavelength of the surface acoustic wave. Right?
Yes, exactly. Yeah.
Yeah.
So you have shown that you can see several ones, and you showed that you can see the fundamental one. I was wondering if you can see the further one of the fundamental one. So let's say that you have a fundamental one at 2 gigahertz. You see
Yeah.
exactly at 6 gigahertz.
So the fundamental one is a little bit problematic because the electromechanical coupling constant is very low. So sometimes you don't see even, let's say, the fundamental zero harmonic. So I think I showed here. Let me see. So here we see in this case we do see indeed the third harmonic of the fundamental still, but it's not so very obvious, but we do see it. And then the third of the second and the fifth of the first even.
Okay, so I see no further questions, so let's thank the speaker.